Good afternoon. This is a talk about dealing with invalid traffic, which is a politically correct way to say things that happen on an advertisement platform that shouldn't. So can be fraud. It can also be bugs from yourself, from the world at large, or from the quirks of HTTP implementation at large. Since it's not another big data conference, there will be some big data in it and some technical details, but we'll start with trying to understand what it is to actually define and act on invalid traffic. And this is a much larger subject. Basically, it boils down to basic software engineering practices. So who am I? Oops. Yann Schwartz. Been working at Criteo for 3 years now, a little more than that. Used to work in a SRE, taking care of Hadoop and streaming, then Kafka. And then I switched to the application side, working on the delivery inside team. This is a placeholder name. Basically, it was just something, so I could call the team Delight. So that's a Delight team, which is responsible for knowing what happens with the delivery. More on what delivery is later. So what we'll be talking about, what Criteo does and what is the delivery. Why is it weird outside? Basically, we're sitting in data center getting HTTP requests from all over the world, and we're trying to make sense of it. And often it doesn't make sense. So we go on with this, saying, okay, we know what's at delivery. We know that there are anomalies in the outside world, and try to see how to deal with the anomalies in a formal or thorough way. And since we are at the big data conference, we'll see how we actually, the things we've implemented for each of those topics. And there will be a fair amount of trolling on streaming frameworks. So don't stay till the end. So maybe by now you're bored with explanation about online advertisement. What we do from the perspective of the deliveries, it's a delivery of the advertisement. It's actually a process which is asynchronous and takes many requests and can last over several weeks. Basically, it starts with a user browsing an e-commerce site, interacting with it, looking at products, putting things in a shopping cart, buying things. And this is the advertiser. This is actually what we're tracking. We're tracking interaction with the user with a given e-commerce site. In our terminology, it's called an advertiser. Sometimes, at some point later, the same user, Alice, goes to another site, which is not an e-commerce site, and which is called a publisher. And at this point, we're asked by different means if, for the current page that's about to be displayed, do we want us, Criteo, to display an ad for the advertiser on the publisher? And the things that are involved there is actually the decision, the information that makes it possible for us to take a decision. So that's a bid. There's an auction taking place between different actors saying, here's the information you have about this user. Do you want to display something? And if we decide to bid, then there will be a display. If everything goes well, Alice will click on our ad, so there will be a click. And even better, after some time, there will actually be a click and a follow-up and a conversion. Conversion depends on the context. It can be just looking at a classified ad, or really buying something. And all this information is fed to our system to make decision over time. So basically, our business model is to get information from interaction with an e-commerce site, display ads only for the people for which we have information, and refine our recommendation and our displays based on further behavior of the user. So this is what we call the delivery. Delivery is basically following all these steps, and from a business point of view, we give money to the advertiser. No, we take money from the advertiser. This is very new for me. I used to be in SRE, so we take money from the advertiser and we give money to the publisher. We buy displays and we sell clicks. So, and how to make this possible? How to actually decide whether to bid and what products, because the ad is about products from the e-commerce side. There's some stuff going on which we won't talk at all here. Prediction models, recommendation models. That's why we have a huge Hadoop cluster somewhere. But basically, this will be widely out of scope of this talk. So those are orders of magnitude. Those aren't exactly the exact numbers. One of the issues we have is this interaction. So the number of interaction of the type just outlined earlier, that's something like around 5 million interactions per second worldwide. Among those 5 million interactions, there's maybe half of them are bids, and then maybe 1 in 10 bid is a display, and 1 in 50 bid or 20 displays is a click. Those are order of magnitude. This means that if we want to make decisions, we have to deal with this kind of magnitude. So that can prove very interesting from an engineering point of view. So that's how it's supposed to go, and I did a very clean, simple, understandable outline of a delivery workflow. The problem with this is that that's how we actually think about the system, and the system doesn't know that it's this way. Mostly, stuff happens. There are HTTP requests arriving on our servers, one of our 15,000 servers worldwide, that there's a specific host for bids, a specific host for display, another one for clicks, and there's a loose coupling between each of those events. So the problem is, we often find that things don't go the way they should go. So there are many things about a web-based internet system that can go wrong or that can be surprising. Mostly HTTP has a long history. One of the reasons it has been so successful is that it was very, very lenient in what it accepted. You have many browser versions, many bugs. So basically, you can't rely on having the client following the standards. You have proxies all over. The direct TCP connection to your server may not be the direct TCP connection to the browser itself. So IP, you can have funny things about IP. You can have headers that are mangled in a way. The mobile web is hilarious in its own way. because you have the mobile ISP that do a lot of strange things for their users to go to the website. You have stuff that are not user but runs. You have a lot of spiders that index content for search engines or do stuff for some mysterious reason. We write bugs. That's the job of a software engineer, writing bugs. So we have our own bugs, and we have everyone else's bugs in the World Wide Web, because we also integrate with other people, partners, brother, and so on. So basically, everything that can go wrong will go wrong. And of course, there are people who are actually being making things work on purpose. They actually want to game the system to make some money. And that's fraud. But actually, most of what I'm talking about here is both something to prevent and mitigate all the other quirks of where we are. And fraud is a specific area of problems, but mostly we have to address everything in this list. Another thing is that the model we saw of our delivery, which is based on actually displaying things to people we already know about and have had interaction with our e-commerce site, and for which we will display more ads, involve conversion, and so on. So basically, we are a bit less likely to be affected by massive botnets, because basically they have to go to website, they have to actually buy things. If we have a bot that buys things, basically we let him. That's the idea is that we're not the lower hanging fruit in our business model for fraud, but we can be affected by friendly fire. I mean, we can be a collateral damage of other schemes, and there are sophisticated ways to try to game our stuff. But everything in that can be a problem for us because it warps the concept of delivery. So our team used to do investigation, help with investigation, detection, so automatic detection, and mitigation, so preventing things to happen again. And so some of these are investigation we had to do associated with. My team, the team I work with, is mostly focusing on tools, way to translate knowledge and wisdom from other teams into executable code. So basically, we have AX data analysts, we have scientists, we have domain experts that try to define what can go wrong, and then we say, okay, can we automate this? The case of the basic clicker is one example of a browser problem. We had displays, so that's normal, and we had a lot of clicks, and a lot of clicks for which we couldn't actually correlate with the display. So clicks without displays, a bit weird. We're supposed to invoice the clicks to our customers, and when this happens, there's no display, so we can't actually do a joint, and there's something fishy going on. We have to actually reimburse our customer, so that's a lot of time lost for everyone. So there's one problem, one violation of our delivery, click without display. It took a while to know what happened because we were using through Facebook, and Facebook, we're not running on Facebook servers, so Facebook gives us the information after a while. So basically, we can't actually look at the data itself. And it happened that there was a Chrome extension downloaded by 20 or 20,000 people in the world that just made the desktop Facebook page look like flat interface. I have no idea why anyone would want that. The thing is, it was doing some CSS transformation, and for some weird reason, wanted to prefetch everything, not using XML HTTP requests. So basically, all the information about the cookie and the referrer were lost. And since we're relying on referrer, we didn't have a click display relationship anymore. And since prefetching is horrible because basically if you have get, it means clicking on everything, clicking everything on the page and following every links, then for us, it appeared that there were clicks. Took us 3 weeks to actually understand what was going on. After that, the mitigation was trying to find how we could actually know that the extension was installed. There was another, this one is a bit weird. We still don't know exactly what it is. Probably not someone malicious. A lot of clicks without displays. Clicks for an unknown partner, so they shouldn't have been there in the first place. And it looked like normal traffic. And when we looked at the HTTP requests themselves, everything was pretty legit, except for a header which had a lower and uppercase spelling. And it was actually something like HTTP underscore something, which is the way PHP mangles the headers when you want to try them at variables. So there was a PHP developer somewhere in the world that maybe tried to do a proxy, did a search and replace on HTTP, forgot to change something and did a mistake. So there was something weird going on, and the only way we could filter this was looking at these weird header. There was also, this one is one of our bugs. Basically, we have an asynchronous way of dealing with Facebook. So we had, Facebook gives us information about the displays afterwards. So basically we got batch, and we had ways to recompute all the batch to simulate them, to simulate the clicks. And for some reason, we were first counting all the clicks for the second hour, then all the clicks for the first 2 hours, and so on. So that's nice. That's n squared divided by 2. So it's a lot of clicks, a lot of money. And it was because we were actually not counting null in a SQL query. That's another thing that looks like our delivery doesn't follow our assumption. And this is another, and that was, what, two days lost trying to figure stuff. You also have, not the loneliest whale in the world, but basically that's the saddest story ever. There's, for the past 20 years, scientists have recorded a whale that's singing at the different frequency that all the other whales in the world. And actually this frequency can't be heard by any other whale. So basically there's a whale that sings alone, and it actually crossed all the Pacific Ocean. So that's someone lost that does thing and no one listened to it. So we had sometimes signals, HTTP requests, random HTTP requests with always the same signature that doesn't do anything meaningful, and we keep having them. So there's just random events, and there's no real pattern to it except the repetition. And then there are the real bad guys. This one, and we had to actually check if it was the case, didn't affect us directly, but it was a very sophisticated botnet, but not botnet, but actually hosting real machines, creating fake publishers, interacting with advertisers like human beings, exactly with the same timing as the human beings, and managed to actually get, the number are not really known, sometime like several $100 million over 6 months, targeting video ads, because video ads pay a lot more money per display than the other one. This one was uncovered by White Ops, so there's a white paper about how it works. The problem with this one is basically the way, if you look at how they investigated and found out, nothing from looking at what was coming from directly to your server could say there's something fishy going on. But this was done by professionals who didn't, I mean, it was a real operation. And this is actually what is called sophisticated invalid traffic. Sophisticated is something that you can't actually spot if you don't have a more global awareness. So the delivery of ads looks straightforward when you write what happens, but for many reasons, because with HTTP-based, HTTP is not connection, because there are a lot of events which are loosely correlated, to make sure that what you see from the delivery is actually what happens, can be a bit tricky. You have the nominal case, which works well. You buy ads, you sell clicks, but what in that, how can you tell that from the point of view of your server, you're just many hosts receiving HTTP requests, what can actually be a signal for a problem going on? So the idea is like, and it's like what we are in a room, and the only elements that are available to us to take a decision is the definition of our delivery. So that's the third slide and 1 million lines of code. That's what the delivery specification is. You have endpoints, so basically HTTP is something listening to HTTP and processing the HTTP request. You have a stream of events because each request will create business events, and you can look at the timeline of those business events. You can save everything, and then you have 80 petabytes of data in a Hadoop cluster, which will take years to read. You have smaller usable data for business analysts. In our case, it's in Vertica. You have other people. A customer saying, why did all my campaign just went in smoke in 2 seconds? So people call us. And you have also the business representative saying that there's an issue with this somewhere in Italy, and so on. So basically, that's the only signal. You have one phone and a Slack channel open. You have Jira incident. You have a lot of information, maybe too much. And what you have to get from this is what's supposed to be, what's invalid in what I have, what's invalid traffic. And basically, it's like a Turing test where you're chatting with someone and you actually achieve artificial intelligence. If you can't tell if the person you're chatting with is a program or human, it's exactly the same, but the other way around. It's okay, we're okay with humans. We don't want to chat with robots, with bugs. So basically, it's how can I tell that someone is not human from looking at bytes? And the first thing, and everything lies on what are we actually doing. I mentioned the delivery. That's 7 bullet points. And those 7 bullet points must be several million of lines of code at Criteo. How can we make sure that it's actually the specification and the actual implementation of the specification? So, and this is actually, this is so common sense, I'm a bit ashamed to make it, but most of the things that could have been code and are now code are based on very simple things. When you're making an assumption, always make assertion. I mean, always verify your assumption about what you're doing. When you have implicit correlation, for one display, there should be one click. Verify this if you can right away. Verify this maybe later on. And you might be surprised and see that sometimes for a display you may have several clicks. Sometimes you can have, for 2 displays, you can have 1 click. But actually you understand more you can understand your business more if you're actually checking your assumption. Something that's very tricky is, and we'll go that later when we talk about blacklist, don't try to list everything that can go wrong. Say what is right. Usually, if do whitelisting, not blacklisting, so define and say, if I want to make a decision, that's what I'm supposed to have. If you deviate from this, there's a potential error. And also, so going on that, define what's nominal. So that's not the same as specification. It's looking at what happens and say, so things are usually like that. We build everything on basically probabilistic model, and we have a lot of data. So let's say, what's a usual ratio between clicks and displays and clicks? If for a certain aggregation of this, we have the ratio is twice or 3 times as much, there's a problem. Maybe there's an explanation, but look at the data, look at the ratio, look at what's supposed to be a normal signal. You have to find the good metrics for that, and look at any deviation from that signal. There's a problem with that, is that everything here looks stupid because it's so obvious. The problem with that is, given the scale of what we do, the cost is not trivial. There's a cost of latency for dealing with anomaly, just like bugs. If you catch a bug in a unit test or catch it 3 months later in production, it will be a lot more expensive. It's the same with those invalid traffic. If you are able to actually not do anything the moment you get a bid, that's great. If you have to have your accountant 3 months later writing a check to a consumer, that will be very expensive. And the problem is it's not even linear in time. It's something, maybe we could have a scientist, data scientist looking at it, but the more it's not square, but it's somewhere between. So between, if you react in 1 second, 10 seconds, 1 hour, 10 hours, usually it's not linear. And when you're trying to build a defense between defense for the problems of your infrastructure and the problems of invalid traffic, you have to think about groups of latency. You have different techniques for dealing, trying to act as soon as possible. So you do basic software engineering, good practice, validate your input. You don't need to have any context. You just look at what's coming in and say, okay, not okay. You can do dumb stream processing. Dumb stream processing is just looking at everything that's going on and not making special correlation about stuff or counting simple stuff with a small cardinality and make decision from that. So maybe the latency here is under a millisecond. The stream processing is maybe a second. You can have more sophisticated stream processing where you're actually looking at events for a window of time. So time in stream processing means memory. So there are limits to what you can do. And if you want to join 2 different events, then it gets really complex. And after a while, it's too complex because it won't fit in memory. You have to look at things for a month, or basically the cardinality is so huge, you're basically writing to disk, and then you batch. So now we're talking about hours, days, or even weeks before detecting something. And usually you'll have mechanism at each of those levels. So stream processing is just a way to minimize the latency. Usually it's dumber than what you can do in batch, because you have very strong constraints, basically on what you can store on the state. But usually you also have almost the same logic in each of those steps. And stream will be more or less, so the accuracy will get better and better, but the latency will get worse and worse. So, okay, so we have, 20 minutes, more than that, 20 minutes about big data. So basically, and the hard part is not writing Hadoop, Spark jobs or writing stream processing, because it's basic engineering with trade-offs. Your memory will blow up, everything will be broken down because there's a dependency problem. But the real hard part of this is to actually know what you're supposed to do and check that you're not doing it. The checking part is not that hard, is actually to define what's nominal. And you have many other ways to get information. You have also external groups that give you data, but that's the really difficult part, is that if you ask two persons in the same organization about the delivery, even at Criteo, you'll have slightly differences between what they say delivery is. So you will make assumption that will get to bugs, false positives or false negatives. So the other thing is actually say what I'm supposed to have, what are the assumptions I'm making, and how do I check those assumptions. So okay, for the boring big data stuff now. At Criteo, we have many levels of information. We have the raw metrics with graphite. I think if you were in the same room, you heard about big graphite. And that's a huge amount of data that can be exploited. You have technical logs, a lot of stuff that goes to in Elasticsearch to die, or you can do full search on it. You have our business events upon which basically our BI or analytics or accounting, billing, and machine learning task is done. So that's strongly typed business logs that are used. Those are the 5 million. There's 5 million business events a second on our platform. You have your humans, the humans at large, the IX, the business analyst, the salespeople, other developers, the people from the escalation team that says that something's going wrong. You have other humans, humans outside of your company that will call because they're hungry because they just got flooded with clicks. And you have other groups of companies that says, oh, by the way, there's a problem with those IP addresses and so on. So those are all the data you're supposed to work with. Usually, what those are, there are way too many to be useful in the first order. Business events and humans are the best first line of defense. One issue with working on a team that's supposed to limit invalid traffic is basically at some point we'll say, no, sorry, this click. We can count this click. We can't charge for this click. So our mission statement is make Criteo lose money, prevent Criteo to charge more. That's a first order problem. At longer term, if we always charge for clicks that don't lead to buys, our customer will stop giving us money. But at some point when we're doing an A/B test, we always know that our A/B test, when we add a feature, we'll lose money. It's not supposed to be 50%. It's a fraction of that. But we can't judge our accuracy on how much money we make. That we may be the only team that says all the team, the machine learning team say that's plus 3% of Regex stack and so on. We just say all the time that we're making, at the best, we're neutral. And there are two ways to do that. You have the slow way. We actually preventing buying ads or counting clicks or counting advertiser events. That's slow and that's accurate. And there's a really fast way to make Criteo lose money is to blacklist everything because there's a bug in what we do, or to blow all servers because we kill the memory, or to blow the whole of Criteo because we killed the SQL server. So this is supposed to be on purpose. This should be avoided. So basically, we're barely tolerated at Criteo, which means that we have a very tiny CPU budget, especially when we're doing the auction. The auction is like we have maybe 50 milliseconds to take a decision. We can't take 20 milliseconds to say, am I going to actually process this or not? We have maybe 2 to 5 milliseconds, which can be huge or not. It's huge if you have to do an outside call. It's not if you can do everything without doing any I/O. And we have a memory budget. So, okay, I'll load everything in a hash table, so that will be fast. No, because everything can be huge. We also have an I/O budget. We don't want to kill the network interface. And we also have an infra budget. I know I'm going to order 1,000 new machines with a nice new NoSQL project that just was created last week. Can't work because you have to. You will have a capex cost. So basically, it's doing this as best as we can without killing Criteo's business. Criteo's business is not charging for clicks that shouldn't be there, but Criteo's business is actually responding to HTTP requests. So we can't have, we should have a very small footprint on the overall infrastructure. So one thing we do in endpoint validation and things, and that's basic security advice, so that's nothing new. When you validate something in input, you don't validate, you don't try to see everything that could be wrong. You define what's good, and anything else you just throw away. Because there are so many ways things can be weird, you shouldn't work like this. Our simple streaming is pretty simple. Actually, that's a bit embarrassing. But basically, we write a lot of code to do stuff like this. Look at the dimension, I count. I look at the metric over a window of time. I group by the dimension, and when this dimension is over something, I block. So it could be, I look for each ID, IP address, advertiser, publisher from the CTR, so the ratio between click and display, over 1 hour. I group by UID, so user, and if they are, and if the CTR is over 50%, this is fishy. I should block. And basically, a lot of things is just that. The tricky part is of a window that will kill your memory, your disk, or you'll have to have a distributed system. The tricky part is the metric. Some metrics are really hard to do. If you want to do a CTR, so you want to have the ratio of the number of click and display, depending on the dimension, it means doing a join. Doing a join in streaming is interesting. And the threshold is also a problem, and that's where we have data analysts. What's the threshold? It's not, we don't know what the threshold. The threshold is, okay, we've looked at all the data from the last year, and if we apply this threshold in the past, then we'll only have 5% of false positives, so that's okay. So this is how much money we're willing to lose, how much legitimate click we want to forgo. And complex streaming, so I won't ask you to spot the difference. It's the same thing, exactly. And we'll go around complex streaming a bit later, but that's basically the same thing, but the metric can be really tricky to have. The window is way beyond what a single machine can do, and so on. A thing about streaming. So, have you heard about, I don't know, I think there must have been a talk about our Kafka infrastructure here. So it's the biggest in some location. It's actually pretty big, and we have a huge Kafka infrastructure for messaging, but it's mostly used to get all those events, those 5 million events a second, in our Hadoop cluster. That's the main point of our Kafka cluster. And since we're in a budget and we try to be as stealthy as possible, we are also using Kafka to do streaming jobs. And we try many things. A while ago, 3-4 years ago, we used Storm. Storm is really nice, but was never meant for Kafka. So there was a very weird and cumbersome conversion between the model, what Storm thought about was stream processing was and what Kafka thought stream processing was. Basically exactly once. Storm works better with discrete events in time. Kafka is meant for, I try to read as fast as I can, a real stream of events. So basically, we suffered a lot with Storm, and for this, we said, no, don't use that. We went the extreme other way. All you have to do is open a Kafka client, just read everything, and do your stuff. Don't use a streaming framework. Your only streaming framework will be read, and that works well. That works well if you don't need to do join, if you don't need to do complex joins, if you don't need to have distributed processing. Actually, you can have that, but that's tricky. And then we tried for complex stuff. Complex meaning we had to look at information for a long period of time. We had to do joins. We had to have checkpoints and be exact about our information. We had to look for duplicate and so on. And we went for Spark streaming, which I'm sure is very nice. It wasn't in our case. Mostly Spark is great for batching, and they had a way to say, look, you can do streaming. You just have to have a 10-second batch and pretend it's a stream. That's my not so humble opinion, that a bit like the problem with Storm. Storm had a different definition of what streaming was than Kafka. Spark streaming is a bit like this. It's pretty much the same thing. So for needs, it was really hard also to extend Spark. Typically, since we're in distributed and we also replicate our Kafka topics, basically you have information coming from many, many different machines, data centers, even continents. So you can't be sure that the message you're receiving, you have all the message you need from the last 15 minutes. So we added a kind of heartbeat, a watermark in every single of our Kafka topics to know what was the latest time we know that we had all our messages. That's a classic problem of distributed system, and also a classic problem of queues. How do I know that I've received everything up to a single point in time? To implement this and to have this integrate into Spark streaming was impossible. Looked like it might have been done in a newer version of Spark, which had a critical bug in Netty and went into deadlock. And we also had a problem with the version of the Kafka consumer that was way too old and was not. So basically, okay, Spark streaming, let's forget about streaming. We went for Kafka Stream, which is basically a dumb consumer with nice little things. So it's a dumb consumer relying on Kafka intrinsics. Works pretty well. We didn't use the distributed windowing stuff because actually it was very taxing on the Kafka infrastructure itself, and we were just tourists on Kafka. The main use of Kafka is to actually import the data. And lately, for the very complex stuff, we've been looking at Flink, which looks very nice, actually, mostly because it's streaming first. And I think they're doing the same mistake than Spark. They actually say, oh, you know, we can do batch also. It's like a stream, but in a batch. So we won't use for batch, but for streaming, it's great. And also, it's a much better concept. Basically, this is Apache Calcite, which is SQL extension for streaming. And in the next version of Flink, this will be supported out of the box. So that's much better than writing your code. Because about streaming, never distribute if you can't get away with it. Never distribute because you'll run into problems. Distributed joins mean having a partition. If you distribute, don't rely on state because you'll run into problem. Okay, if you have to rely on state, don't rely on only once delivery. Do the duplication. Either don't work without duplication, have idempotent process, or do your own deduplication. Or if you need everything at once, at some point stop doing stream processing and say, okay, I run a Hadoop job in an hour because this is too much. I'm going to need 100 servers to do that. This is not worth it. Of course, the problem is the limit, the frontier where you should go, just stop streaming and start doing a dupe is not that clear-cut, but that's the idea. I'm so good with it. About blacklist, basically blacklist is a simple thing. We have a list of UIDs that are strange. We have a list of IP addresses we should block, and so on and so on. At some point, since we are on a budget, we are really on a budget, and we have to ask, okay, how many memory can I use for everything I'm doing? And usually say, okay, let's go for 50 megabytes. And I have to cram everything in 50 megabytes. So if my data structure is just more than 50 megabytes, enforce it in code. So never load the data structure. If you're over, I don't know, 50 megabytes, say, okay, I'm not loading anything else, or just say, I'm crashing, I'm not working anymore. And if you go over there and you still need to work, go probabilistic. You'll say, okay, I'll say that it's likely to be a problem, and then we can use fancy little data structures to still be able to blacklist and sometimes to miss. And that's one of the really nice things about working in this team, is that maybe one of the first time in my professional life where I had to actually look up an algorithm. And when hash table was not enough, so I don't know, to do multiple string match. Typically, to blacklist user agent, you have the Hao Kozaki algorithm. You could also write a huge regular expression, and then you would kill your server. So we have a deterministic. We are sure about our CPU budget, and we are sure about our memory budget. Radix trees, basically we're doing what do routers, because our IP list, blacklist are by subnets, and we do what we do routers, and routers use radix trees to have a constant time to look over many subtrees. Bloom filters, Bloomier filters. Bloomier filters are Bloom filters, which are kind of like hash tables, and where you can count and not count, but actually delete items and so on. So basically, what we get there with Bloom filters is that it say, okay, we're gonna cap the memory, we're gonna cap the error bound, and we negotiated with product. We say once every 10,000, we'll say that something is fraudulent, even if it's not. So we will blacklist innocent stuff. That's 1 over 10,000. There's a missing point. We're using Kafka. Since we have many processes, stuff that detect, we're using Kafka for every of what we call a predicate. A predicate could say, this UID has a problem for those reasons, this IP has a problem for those reasons, and everything is just sent to a Kafka cluster. Everything is read from servers that serve this to the front ends, which will enforce the blacklist. And we're actually using, since for some reasons it's hard to have distributed file systems in some of our data centers, we're also using Kafka as a file system. We just look back in time and reread to read our list. So yeah, to two funny things we did. We did a worldwide A/B test about fraud. For some horrible bug, we stopped delivering any picture for ads. So we had blank images all over the world. So that was ad blocker as a service. And it was for 45 minutes. So for 45 minutes, any Criteo ad, so that's a lot of ads, were just a blank image on screen. And we looked at that and said, maybe we could make something out of it. So basically, we are displaying a lot of blank ads. What if we looked at the clicks we got during that period of time? So yeah, there may be people who click on blank. That's possible. You also have the people on mobile. Basically, a lot of clicks in mobile is just people with big sums. But there should be a signal here. So basically, we're actually looking at the data. And it's a bit more complicated like that because there are caches all over the place. But this is a good way to know what's actually fishy in our click stream. And we also had another way we didn't go much into that. It's more the inventory quality. Basically, you have publishers which display our ads. One way to make money is to be a publisher, to be paid. So let's look at the publisher. Can we do a static analysis of a website to know if it's likely to be a web content farm and so on? And what we did is we farmed a lot of URLs, went with these URLs through a list of fishy sites, and we display the site and we ask a human being to say, do you think it's fraud or not? So that way, we can actually label things to do actual machine learning, because the problem with machine learning is we don't have labeled data. You don't have labeled timelines. You don't have labeled sites. So that was a way we were doing Mechanical Turk Criteo-wise. We did that for our team, and we're maybe gonna launch that. So basically, there are 50,000 sites will be done in a week or so. And from this, we can use. We also do classic anomaly detection on signal using looking at the signal and changing. But this is basic stuff. You can have those in metrics. So to make most important thing, know what's possible and what your model is. So basically, be sure about what your system is doing. Verify all your assumptions, question them, and if you're sure of their assumption, write a session about them. Defense in depth, basically do the same thing, but different level of details and different level of latency. In streaming, in complex streaming, in Hadoop batches every hour, in Hadoop batches every month, and so on. The kind of checks will be pretty much the same, but we'll get more and more precise the more latency you have. But you can't do everything in streaming, and if you want to do everything in batch, you have 24 hours delay before reacting to your problem. And stream processing is fun for every definition of fun, so fun and horrible. So that's where writing something that can be written in one line of SQL takes months. That's a lot of fun. And distributed stream processing is really, really fun. And that's it. And I'm awfully late, so maybe Ed, if you have any question, ask them to me, and I think you can have a coffee and breathe a little. Thank you.